Which are commonly used for TC.
So this was quick thing.
Yeah.
So like when we we were doing the quick before.
Okay.
And like that's like the one programming space where we have to go a bit more comfortable.
Okay.
And now this is the whole new other thing. So I
Okay.
wanted to know like
Yeah.
the paper quizzes. Would you ask like coding stuff or
In the exam, you mean?
yeah.
Yeah. Okay. I will talk about this again. I think I at one point I mentioned, but let me quickly talk about this for the whole one, because I think this is a question that's very common among all of you.
Yeah, because the thing is,
Yeah.
like even if it's a lab, like I know
Yeah.
what to do with the codes.
Okay.
It's just that I don't know how to actually write it down because like
I
I'm
see.
more accustomed with the C++.
But you're writing, but you're also writing C, right?
Yeah, we're writing C,
Okay.
and like, but like, it seems a bit different compared to how
Okay.
we did in the
Okay.
24 one.
I see.
So like we used to use Trish D bits and everything over there.
I see. I see.
And
Okay.
like, so
Yeah.
that's what like very confusing about me.
No, okay.
And it was since it was an open book over there.
I see.
And so that
Oh, 241 was open book.
241 was open book. So that's why, like, I was asking whether, like, it's going to be coding or like,
This is very interesting to be a second year course and it's open book.
yeah.
Very weird. Okay. Okay. I will talk about this.
No worries.
Okay. So for everyone, I think we are already late. It's all right. But just give me 1 minute because the projector is not really working. Yeah. For each machine, and then scale each row based on the field of that row and standard deviation of that row. That would be I don't know. So it's these four row running. These mean the equations are basically I ask you to release him that we start reading. Good morning, everyone. Assalamu alaikum. So as we promised last time, today we're going to go through a few of the example scheduling questions. Very good. But before this, I would like to comment a little bit about, again, maybe I have already said this in the past, but just as a reminder for everyone and see if this same concern exists in any of your minds, right? So you're asking me again about the exam, right? And the style of things and how different things are from 241, right? So as I mentioned earlier, in the exam, this is not a lab setup. So I will not ask you really to write a lab code, right? Like you will not ask you to write a program that will take like a couple of pages, because I don't think and I don't believe the exam is the right time to ask you to code, right? Lab is the right setting there, and the project and the demo is all about really hands-on. In the exam, though, we want questions that would assess your understanding of the course, including also the C, which is part of the again, we are looking into it from a system perspective, right? So we covered embedded C programming, but the questions would be more like what I gave you in the exercise question. Like I give you a piece of code, I ask you to trace things related to closer to embedded than general C programming, like again, pointers, bitwise manipulation, maybe arrays, things that you will face in the lab in every day. So if you have done the lab yourself, they will come very naturally, right? Like you will just basically, you will know the answer without even thinking about it. Good. That's with regard to programming, because I received this question multiple times. Is that clear enough now? Like no one has concern about being asked to write programs in the exam? Good. Then for the other questions, I also like a lot to be more numerical than theoretical. Like I'm not a believer of writing essays in exams, right? Because this is engineering, not history, not social studies. This is engineering, right? So as much as I can, I would try to squeeze and extract numerical questions from the material we study, right? Now, some of you might see that this course, there is a lot of theory and slides and heavy drawings. And this is in fact intentional because this is a fourth-year course. It's more important that you get practical knowledge and knowledge that is more about engineering assessment. Then I would just basically say, okay, here is like in the lecture, we know how we solve these questions in that way. You kind of memorize it or you know how to solve it and then go to the exam and solve it, right? With all respect, that's not education, right? I mean, I don't want to teach you how to solve questions, right, in the exam. I want to teach you how to make design decisions when you go and work. Because again, that's fourth year, not second year, not first year. Good. Now, the exam is also not open book because whether it's open book or not, as I said earlier, it doesn't make it any easier for you. In reality, I always believe open book exams are the hardest, right? Because again, if I know that you have access to everything, I would have to come up with something that would really test you, right? So in that case, I would test you with the knowledge that you have access to all the material, right? I don't think you would like it, right? And I don't think open book exams are suitable for all types of courses. Mostly I've done them in the past in graduate courses, not in undergrad. Some other undergrad courses might be suitable, right? But not this course, good? So, and it's not because the exam is going to be harder or anything. It's because I think it's in fact more suitable for the exam type of knowledge we cover, and also for less stress for you in the exam, right? Do we need any cheat sheets or anything? No, right? Again, I don't believe that you should memorize any equations or anything. I don't depend on that. There are things that should come naturally to you. If you know how to think about things like what we have done in lectures, even if there is like some sort of an equation, you should be able to drive it in a minute, right? Again, utilization stuff and stuff we discussed, right? So I've in this course, I've been teaching for many years. I've never thought I need really a cheat sheet, right? Because again, I go away from formal groups, right? This course sometimes really is heavy in math, like how you drive, for example, the utilization bound for RM and etc. I go away from this as well. I just do this in the graduate level. With what else? With regard to the quiz, our first quiz is in week 8, which I think is not next week, the week after, right? This is just a reminder that the week after, let's say on Monday, we're going to have the quiz. The quiz time is, let's say, half an hour, right? 20 minutes to half an hour. I still need really to put in things in place. It might be less, it might be 15 minutes. Again, I will give you more information next week, but it's most likely a single, like, numerical problem, right? Like something that you should be able to solve in 15 minutes, 20 minutes max. Good. Yeah, is there anything else? What type of question? Again, you have the exercise questions on either. Make sure you solve these, solve the ones. If you ask me for a recipe for study for this course, start by lectures, and then simply any additional tutorial or exercise problems we solve, like the one we're going to do today, and then go to the exercise problems I share with you, try to go through them before you open the solutions. There is a reason why I spread the solution from the exercise, right? In fact, it takes me more time in ethics to prepare, but I give you the questions without the solution such that you open the document, try to solve yourself, and then try to look for the solution for things you don't know, right? Just activate those neurons in your mind that you need to think about the problem before you look into the solution. Great. And then if you're not able to really understand any solution, come to the office hours and we can discuss. Yeah.
With one, which classes or lectures?
Yeah. Well, it will be up until what we covered in quiz 1. I should also give more information next week. I don't think we will include scheduling in that quiz because I want to keep it for later quizzes. But I will let you know next week. I will let you know up until this lecture. This is quiz 1, and then this is maybe also quiz 2. Because in reality, starting from week 8, we're going to have a quiz every couple of weeks, right? So we have 2 before the midterm, and then the midterm, and then 2 after the midterm. And the midterm will be in class, right? So it will be during the lecture. Anything else? Is there any other question that comes to your mind? is bugging you there about the course and you're concerned about it?
The project.
Yeah, for the project, this is more with Salsabil, but you need to start thinking of what you want to do. I think Salsabil did she already share with you a few ideas because we have been exchanging emails for ideas. Okay, so we should do this week or the earliest next week. But you can also come up with the ideas your own. You already know what we have in labs. There weren't really servos or DC motors in the lab, but I ordered some, so we're going to have those as well. If you want to do a project that includes these, we have cameras, we have Raspberry Pis, in addition to the ST port, right? So you want to make sure when you come with an idea, you have a way to execute it, right?
Yeah.
In the first milestone, what you are asking is what is your idea, and simply what components you would need. That's really all, right? It's just more of like a milestone that asks you, okay, are you really, did you make your mind about what you're going to do? Are you all in agreement as a group, right? So you share your group name, the idea, maybe a schematic if you came up with one, that's good. And then the components you need. And then we take it from there one by one, right? You are not really asked to do another senior design project, because there is no time for this. So it doesn't have to be very big. And you're also, don't expect you do like a simple 3-hour lab, right? So don't really go to the other two extremes. Build something that you yourself will be proud of when you put in your CV, right? Something that opens door for you and something that will make you simply apply what you have learned in lab and in the course. Okay, did I answer you?
Is it okay if you can give us some sample ideas?
This is, if I thought this is already shared with you this week. If not, then early next week, we should receive a document from Salsabil, including some example ideas, right? Because again, we have been discussing this in the background and we will give you a few ideas. And feel free to talk to Salsabil and to me if you have an idea in mind and some of you already did this. If you're not sure if it's very feasible or what to expect, come talk to me or Salsabil and we can guide you, yeah?
If in the exam, if we have like theory questions, can you just make them multiple choice?
Yeah, I mean, again, it depends on the type of the question. Sometimes I ask multiple choice questions if they are theory. Sometimes I ask you, for example, and a typical example we have seen last time from one of my earliest exams is list the trade-offs between interrupts and polling. That's something I cannot really ask in a multiple choice question, right? So it depends really on the nature of the question, right? But again, put in mind that even if I ask you a theory question, I'm not expecting you to spill over exactly what I've written in the slides. You guys are not like memorizing machines, right? You are engineers, you have your own mind, express things in your own language. I always appreciate this, right? There is nothing to memorize. If you understand something and then you give me like keywords that I know what you're talking about, that's all what I'm looking for, right? So don't get very concerned about theory questions as far as you know what is in the lecture, right? Again, we give you the recordings. Hopefully, most of you that I see now are really attending all the lectures anyway, right? But you have access to the lectures, to the slides. If you know the material there is no need to worry. Good. Are we good? Great, thank you. So now let's go and try to solve few scheduling problems. I already uploaded these slides on iLearn for you if you want to take notes. What I have done, especially for this one, is there is a clean version that is empty without the solutions. We go through the solutions together, and then after the lecture, I will upload the one with the solutions. Okay. So let's start with a very simple example. Assume we have a system with 3 tasks. These are periodic tasks, tau 1 to tau 3. I give you the completion time, the deadline, and the period. And then I first start by asking you, what is the CPU utilization, right? This is fairly easy to calculate. You basically take C over D for all the tasks, you sum them up, and you come up with the utilization. Over T, C over T. Yeah, oh, did I say C over D? No, it's C over T for sure, yeah? Because the T is where the task repeats, right? And then you calculate the utilization. Even if you're not asked in an exam to calculate the utilization, I would highly recommend you do it. Why you do it? Because it can guide you, for example, in rate monotonic, whether those tasks can be schedulable or not. In one of my exams in the past, I gave a tasks, like number of tasks that basically their utilization exceeds 1. And then I asked the students to draw an EDF example scheduler. You cannot imagine how many of them, in fact, try to draw an EDF, right? I mean, if you just exceed 1, you stop. In less than 30 seconds, you are done. You don't need to do anything. You just tell me this, I'm not schedulable using EDF for anything else, right? So if you start with utilization, you know what are your limits. Can this be done using RM? Are you sure? Not sure? Can this be done using EDF? So it can guide you. Then after you calculate the utilization, here I ask you, can you schedule this using fixed priority schedule, right? and what algorithm you are going to use and why, right? Maybe we should start, right? Oh, I already gave you the answer, which is bad. So simply, if you look into these tasks, you find that the deadline and the period is not the same. So rate monotonic cannot be used here, right? Rate monotonic, because rate monotonic assumes deadlines and periods are the same. Instead, you want to use deadline monotonic, which is just simply exactly rate monotonic, but assigning the priorities based on deadlines, not based on periods, right? So you use deadlines, you use deadline monotonic because deadline is not equal to the period. Now, if you want to schedule this using deadline monotonic, what do? Simply you start by looking into priorities. Which one has the highest priority here? One, is it? Tau 3. Tau 3, exactly, because it has, so this is the highest priority. Then the one after is Tau 1, Tau 2. So simply this is how you assign priorities, right? And then if I start by Tau 1 and I have a single CPU, so I can start by scheduling Tau 3. Now I'm putting all of them in one diagram just to show you how the CPU is executing. But in the exam, it will be easier for you to do what we have done really in the past by splitting the tasks, right? So this is Tau 3, this is Tau 2, and this is Tau 1. For fixed priority, again, before you even start doing anything, just put in the task information on the diagram, right? For Tau 3, I have a period of 5, right? So you simply say, okay, here there is an interesting point at 5. There is another interesting point at 10, at 15, and at 20. Right? And then you also put in your deadlines. You have a deadline for Tau 3 at 3, right? So this is your deadline. This is 3. This is your deadline. This is 0, 1 for the first. Oh, sorry, it should be 0, 3. And here should be 8, right? The second deadline. And the third one should be 13. And this one should be 18. I did. Oh, is it not visible on?
No, I haven't.
Oh, you guys are okay. So it's 3, 3. So what I did now is I did not solve anything. I just really put in the information, right? I can do this for all the tasks. And then for Tau 2, I have a period of, so Tau 1 first, which is the highest priority. So it should be Tau 1 and Tau 2. You can put it in any order, but in reality, I just facilitated for myself that I put the highest priority first, then the one after, then the one after, right? Because it can help me really focus. Remember, in fixed priority, you can schedule the highest priority regardless of the other ones, right? So start by the highest one. And then for Tau 1, you have, again, a period of 4. So here you have 4, and then you have 8, you have 12, and then you have 16, and then you have 20. For Tau 2, you have a period of 15. Ouch. So we need to go up until what is going to be my hyper period? No, the hyper period. The hyper period for our schedule. Oh, the hyper period is always based on the period, right? Because this is how things repeat, right? So now we said the hyper period is the least common divisor. So we have 4, 5, and 15, right? So this gives you 60, I think. Is it? 60. Because 30 doesn't work for 4. Yeah, it has to be 60, right? So you go up to 60. It's interesting. And then, well, if we made this 12, we would basically have, no, but even 12 doesn't really work very nicely, right? Okay. If I make it 20, then we stop at 20, right? Okay, so just for the sake of solving in the lecture, let's make it 20 for now, right? This is for Tau 2. Then I basically repeat 20, etc. And then I have a deadline of 12 still as is. So now putting the deadline for Tau 1 deadline is 4, which is equal to the period. So again, that's easy. Like this is your deadline for 0, 1, 1, 1, 2, 1, 3, 1, and then 4, 1. And then for Tau 2, I have a deadline of 12. So this is basically the D02, and then the one afterwards comes at 32. Good. So again, what I have done so far, I just put in the information I have. I did not really solve anything, right? Now we start solving. fixed priority, the trick we said last time, start with the highest priority, don't worry about anything else, right? Tau 3 is the highest priority. I arrive at time 0. How many computation units I need? I need 2, right? So I basically run for 2 here. So this is up until 2. And then I arrive at 5. So I run from 5 to 7. And then I arrive at 10. So I run from 10 to 12. And then I arrive at 15. So it's 15 to 17, right? So simply, this is executing Tau 3. Okay. Now, in executing Tau 1, which is the next one, I simply cannot start up until 2. How many computation units I need? I only need 1, right? So I run from 2 to 3. And then I arrive every 4. So simply I run here. I mean, between 4 and 5, I can run, which is good. And then at 8, I arrive also. So it's 8 to 9, I can also run. And then I arrive at 12. 12 is empty. Oh, that's also nice. So it's 12 to 13. 16, I am busy. So I can run from 17 to 18. Good? Yeah. Yeah, but for Tau 1, the period and the red line is equal. Yeah, because if you look here, like the red line and the period for both are equal. Yeah, it's the same point of time. Yeah, but again, we repeat every period regardless of the red line. Yeah. Any other question? Are we good? Okay, now for Tau 2, you are just left with the leftovers, right? Like you basically whatever left from the CPU you need on. From 0 to 3, it's busy. 3 to 4, the CPU is empty. So in reality, I can run from 3 to 4. That's for Tau 2. So I run from 3 to 4. And then 5 to 7 is busy. 7 to 8 is empty. So I can run from 7 to 8. How many computation units I need? 3. Okay. So 7 to 8. Not yet, because your deadline is 12, right? And then 7 to 8 is done. And then 9 to 10 is also empty, right? So you can also run from 9 to 10. Right? And then you are done with your 3 time units up until a new period, right? Okay. Assuming we changed our period to 20. Is that clear enough? Now, to know whether you are schedulable or not, you need to whether you really finish your full computation before a deadline arrives, right? That's really the main point. Did we meet our deadlines here? The answer is yes, if the period is again 20, because we are just basically making it easier for us to hyper period. Are we good? Now, if we are using EDF, how this is going to be different, right? Yeah. Again, I will share this with you, so you don't need to worry, but yeah, that's okay. So now, if we're using EDF, by the way, if you look into this diagram here, what I've done is just basically combined everything, right? 0 to 2, you are running Tau 3. 2 to 3, you are running Tau 1, right? This is how the CPU will see things, right? This is split for tasks for our easier handling, but this is how the CPU is really executing. Okay. Now, if we run things using EDF, so let's go through the drawing together and see what really happens. So for EDF, again, maybe we should really do it ourselves because you guys will be confused. So EDF, based on what I assign priorities, is dynamic, right? So I really don't know. It all depends from every job to another job. But I still can really draw in periods and deadlines accordingly, right? So for Tau 1, here I just do it in order because I don't know which one is highest priority. Tau 1 has a period and deadline of 4. So again, I have 4, 8, 12. Let's still make this 20 for our sake of easier analysis, and then 16, and then 20. For Tau 2, I simply have 20, and then I have a deadline of 12. And for Tau 3, I have a period of 5, 5, 10. Usually people represent the activation time of periods with this upper arrow, okay? And the deadline is usually with this down arrow, right? And then 5, 10, 15, and then 20. And I have a deadline of 3, right? So my deadline is 3. This is 0, 3. And then I have 5, which means it's 8. And then 10 and 3 is 13. 5, so it's 18. Are we good? Same thing we have done in the past. In fact, I did not really solve anything yet, right? Now let's start solving using EDF. So in EDF, you look into job by job scenario. At time 0, I have 3 jobs, all of them arriving simultaneously. Tau 01, 02, 03. Which one has the earliest deadline? 03, right? Because it has a deadline of 3, right? If you compare, we have 3, and then we have 4, which is the deadline, and then we have 12, right? This is 12. So Tau 03 is the highest deadline, so I start with it. How much competition units I need? 2. So you run from 0 to 2. Now at 2, you need to make a new decision point between Tau 1 and Tau 2, Tau 01 and Tau 02. Which one is earliest? 01, right? So you basically run it, and you run it from 2 to 3. Now I stopped at 3, despite the fact, oh, Tau 1 is also just one competition unit, so it's done. At 3, how many jobs do you have to choose from? Yeah. Yeah, exactly. You have a one from Tau 2, and I have a one from Tau 3 that just arrived at 3. Which one do you pick? The one from Tau 3 has a deadline of? Oh, my apology. At time 3, nothing arrived really from Tau 3. That's not correct, because they arrive based on the period, right? So you have the new job here arriving at time 5. So the only job you have to execute is in fact from Tau 2. So from Tau 2, you execute it for one-time units between 3 and 4. At 4, it is where really a new job arrives, which is simply Tau 11, right? It's not that you break it down, it's you start executing, but then when something new arrives, you recalculate the decision to see should you continue or should you preempt, right? So this is why 4 is in fact a decision point. Now between Tau 02 and Tau 11, which one has an earliest deadline? So now at time 4, you are choosing between Tau 1 and Tau 2. So it's Tau 11 because it has 8, while Tau 2 has a deadline of 12, right? So that means now EDF should really switch to execute Tau 11. So I execute Tau 11 from 4 to 5. And at 5, how many jobs I need to choose from? Tau 2 and Tau 3, exactly. Which one has an earlier deadline? Tau 3, because it has 8 and the other one has 12. So now you switch and execute Tau 3 for 2 time units from 5 to 7. Now at 7, what other jobs I have? Tau 2 is the only one, right? So you execute from 7 to 8. And then you're still really left for one competition unit. But in reality, you have now 3 jobs to choose from, right? You have a one from Tau 1, which is Tau 2-1. You have Tau 02, which is still running. And then you have, no, like Tau 3, nothing arrives yet, right? It arrives here. So you have between Tau 2-1 and Tau 2. Which one I choose? Well, let's think. For Tau 1, what is the deadline? 12. For Tau 2, what is the deadline? 12. So they are equivalent. What decision do we make if they're equivalent? You continue with the one that you are running to minimize context overhead, right? So simply at 8, you continue with Tau 2, and you run for 1 extra time unit because you only need 3, right? So at 9, I'm done really with Tau 2. What jobs do I have? It's only Tau 2-1, and it runs from 9 to 10. Now at 10, what jobs do I have? It's Tau, this is Tau 1-3, and this is Tau 2-3. So you have Tau 2-3, it should run for 2 time units. So you run from 10, and nothing arrives up until 12, so you are good. So you finish 12, and you are done with it. Now at 12, what do I have? You have a new one from tau 1, which is tau 3.1, right? That's the only one you have. So you basically run it for 1 time units at 13. At 13, what do I have? What do you think? But tau 3, does it have anything? Idle, exactly, right? No jobs are ready. If you think at time 13 here, yeah, if tau 1 simply at 13 is done with this job. Nothing is arriving up until 16. For tau 2, nothing is in fact arriving up until 20. For tau 3, the last thing arrived at 10 and it's done at 12. So at 13, nothing really can improve, right? Okay. Yeah, so I'm in fact idle from 13 to 15, right? And then at 15, tau 2, 3 arrives, so it can execute, right? And it needs 2 time units. So basically it runs from 15 to 16. I cannot say 17. The reason is at 16, a new one from tau 1 arrives. Which one has an earlier deadline?
Okay.
Yeah, this is the reason why I really always draw them, right? Because it's easier to just calculate while you're solving. This is 18, this is 20, so you continue with this one. So you run it from 16 to 17. Or you need 3 time units, in fact. So you run it from 16 to 18, and you are done, right? Tau 3, oh, sorry, 2 time units. Okay, how do I, let me see. What did I do? So we said tau 3 is how many time units? Oh, 2. So you can only run from 15 to 17. Seventeen to 18 is tau 1, right? Because that's a 1 arrived at 16. So 16 to 18. You run it for 1 time units. At 18, do I have anything? No. In reality, from 18 to 20, you are idle as well. Good. Make sense? Okay, so summary is start by putting in all the info here, deadline and periods, because this can really help you solve. And focus on your decision points, right? Focus on when you need to make a decision. You always need to make a decision when a task is done or when a new task arrives. Other than this, you continue, right? Good. Now, this is another example. We basically changed the computation time and deadline to make them unschedulable using fixed priority, if I remember. Let's see how much time do we have. Okay, so assume now we change the task set into these ones. And simply, are these ones scheduled using deadline monotonic? First thing I do, what do I do? Yeah, the utilization, right? You calculate your utilizations. Now, if you calculate your utilization, you simply do 1/2 plus 2/3 plus 5/16. If you calculate this one, you will find yourself, in fact, larger than your 2 to the power 1/3 minus 1, if you do the math, right? Again, in the exam, you would have a calculator. No, it's always C/T. Oh, did I do? I keep doing the same mistake. So it should be 5, and this one should be 4, and then 20. It's always C/T because, again, utilization meaning is how much computation I take every watt, right? So if you do that math, you'll find yourself larger than this value. What does this tell us? No, that's wrong. We don't know exactly. That's very important because if it's not schedulable, you not even try, right? So we don't know, right? So you have to try. Now, when you try, if we repeat things as we have done, let's start. Which one has? Let's first assign priorities. Which one has higher priority? That's quite easy, right? Tau 1, and then 2, and then 3, because 2, 3, and 16, right? So now you start at time 0. Tau 1 has a higher priority and it arrives every 5, right? So you find that at 0 you execute it, at 5 you execute it, at 10 you execute it, and at 15 you execute it. Every time you execute it, you require one time unit, right? This is basically this repetition of Tau 1. Okay? Then you go for the second one, which is Tau 2. Tau 2 arrives every 4 and it requires 2 time units, but it can only execute after Tau 1, right? This is why it waits for 1 and executes for 2 time units. And then it arrives at 4. At 4, there was one, maybe. Okay, let me try to draw it for you because otherwise. So simply what we said is we start with Tau 1. And Tau 1 is the one that was the highest priority and it arrives every 5, right? So you have 0, 5, 10, 15, and then 20. And then let me try to align this one with this one. So I put 15 here. And then for Tau 2, so this is Tau 1, right? So this is Tau 0, 1, Tau 1, 1, Tau 2, 1, Tau 3, 1, and then Tau 4, 1. Every time I arrive, I would require one time unit and I'm the highest priority. So I should schedule myself independent of others, right? 6, this is 11, 16, then it's 21. After 20, we don't need to worry. So now I'm done with Tau 1. For Tau 2, well, I arrive every 4. So I arrive at 0, and then I arrive at 4. This is Tau 1, 2. Arrive at 8. It's Tau 2, 2. And then I arrive at 12. Tau 3, 2. And then I arrive at 16. It starts becoming messy, right? This is why we split them. So it's Tau, we said what? 3, 2, and then this is 4, 2. Now, when I arrive, if the processor is busy with Tau 1, I have to wait for it, and I want to execute for 2 time units. So you execute from 1 to 3. And this is basically this is Tau 1, this is Tau 2. And then you arrive at 4, from 4 to 5, CPU is empty. You still need 1 time unit, so you can execute it from 7 to 8, from 6 to 7. I think you can see now, if you try to put everything on the same diagram, you guys might get lost, right? This is why we split it between tasks, right? But just for sake of space, and you already know how to solve it, I'm just really showing you the diagram. So we schedule Tau 2 here for 2 time units. Here at 4, CPU is empty, so 4 to 5 I execute it. 5 to 6 is executing Tau 1. So 6 to 7, you go back to Tau 2. So this is Tau 1. Now I also arrive at 8. From 8 to 10, I'm empty, so that's good. This is Tau 2, Tau 1, Tau 1, Tau 1. Now after 8, I arrive at 12. Again, I'm empty, so I execute for 2 time units. So it's 12 to 14. This is Tau 2. And then I arrive at 16. So 16 to 18, again, is Tau 2. Make sense? Yeah, the diagram might be a little bit confusing, but again, and depending on the fact that you know how to split, right? So the only thing is I start with the highest priority, fill in the diagram, then go to the second one and fill it in based on whatever Tau 1 was busy. And then I go for the last one, that's the one that's least lucky, right? So what I do is I only choose the empty slots there and see if I miss my deadline or not, right? That's the key idea. For Tau 3, you basically arrive every 20, so you only arrive once within this diagram, but you have a competition unit of 5 and your deadline is 16. Now, how many slots do we have? We have 1, 2, and 3, and then 4, but I require 5. Oh, you have to stop at 16 because your deadline is 16. So this is why you miss your deadline, right? This is why you see here Tau 3 executed for 1, 2, 3, 4, but then deadline arrives and they still have 1 competition unit. So you miss your deadline. Good. This is an example of missing a deadline because deadline monotonic did not really work. Yeah.
If the tasks are, if we don't know if it's schedulable or not by deadline monotonic, why not just give up from that start and find another algorithm that can schedule it eventually?
In practice, you might, if you would like. There might still be reasons why you want to use deadline monotonic or RM because they are easier to deploy, as we said last lecture. In question, that's part of the exam, is to see whether you can really get a schedule or not, right? You know what is the next step. If you ask me, like what happens really in practice is that there are those static analysis tools that they try to come up with schedule instances.
Yeah.
They first try the utilization bound. Your best case is you use an algorithm that from the beginning is just easy for you, tells you yes or no, clearly.
Exactly.
So in this case, you don't need to worry. But if you are using simply a non-necessary condition, then you have to try. And what they do is they try and they stop at one of the 2 points. They either miss a deadline or they find the schedule instance. Because in both cases, you are sure that you are either schedulable or not, right? Make sense?
Because it's very unstable if we don't know if it's schedulable or not. Maybe if we add in something like aperiodic tasks or dependencies, it will.
True. But all the time, your answer to the schedulability analysis, assuming you know your task set.
Yeah.
I think the point you are bringing is another interesting point, which is what if my task set is dynamic? And this is in fact a topic on its own in real-time systems, how to account for dynamic systems. There are ways to do it. But all what we study in this course is that you start with a known task set. Okay? Yeah, I think for you it's easier. To me, both answers are correct. It doesn't really matter. Yeah, to be honest, sometimes, most of the time I see students prefer the one split because they are easier to put in arrows and the stuff, but both are correct. I mean, if you are more, if you find it easier for you, for example, to put one diagram, then just put one diagram. There is no problem. Okay. Do you have any questions? Okay. Now, can we do the same thing for EDF, right? Are those tasks schedulable using EDF, right? So, yeah, maybe I'll just again I'm trying my best that we do it from like together from scratch. So just basically see how to think about the problem, right? So, what is that? Can you? Oh, you want to split them? Yeah, let's split them. That's okay. I think we have enough space here. So this is tau 1, tau 2, and tau 3, right? And then again, just systematically, I do the same thing. I have 5, I have 10, 15, and then 20. And then I have deadline of 2. And then deadline of 7, 12, of 17. For tau 2, I have a period of 4. So it's 4, 8. Just like a note, when you split them, make sure you align them, right? Because if you put 10 in one place and there is no point, I mean, you lose your track, right? And then 12, and then 16, and 20. And then for tau 3, you just have 20. Here, the red line is 3. So it's 3, 7, and then 11, and then 15, and then 18. Here, the red line is 16, which is this one. Right? So again, put in deadlines and periods in all the tasks. Now let's start. At time 0, I have 3 tasks in my system. Which one has earliest deadline? Tau 1. If you look into all the down arrows, this one comes sooner, right? So you just start with it. So I want to execute for 1 time unit, so I run from 0 to 1. At time 1, I have tau 2 and tau 3. Earliest deadline is tau 2, right? Because it comes first. And then at 1, I want to run it for 2 time units, so it runs until 3. So I barely made my deadline, right? Now at 3, you are done and you only have 1 task. So you run tau 3 from 3 to 4. Why did I stop at 4? Because you have a new arrival here. Now, what is the deadline for this one? It's 7. The deadline for this one is 16. So you should really switch to this one. From 4 to 5, I execute this one. I stopped at 5 because I have a new arrival here. This one has a deadline of 7. This one has a deadline of 7, right? Again, by putting it visually, I don't even need to think, right? Just continue with the down arrow, right? Like see things. So the down arrow is aligning, so I continue with this one. So I run it to 6. Now it will be, C is in fact not a factor. C is not a factor in EDF. What really matters is the deadline. Because remember, EDF assigns priority earliest deadline first. There are other algorithms that in fact would take into account how much competition you would need, not EDF, right? So don't worry about C at all. Now at 6, I'm done with this one, but I have a new arrival here and I still have tau 3 to finish. Which one has earliest deadline? Yeah, tau 1, because simply it's at 7. So I switched to tau 1. So I run it from 6 to 7. And again, I barely made it. Now at 7, I only have tau 3. So I go back to tau 3. I execute up until 8 because I have an up arrow back then. So at 8, I have this one and this one. Which one has earliest deadline? Down arrow is here, down arrow is here. So it's definitely tau 2. So you switch tau 2 and you execute for 2 time units up until 10. You can tell it's very, very systematic now, right? I'm even like not thinking much, right? Looking into things and systematically execute it. From 10 to 11, quickly then. And then at 11, tau 3. Now you have tau 2 arriving. So simply, yeah, because the deadline is 15, while this one is 16. So you execute tau 2. So it runs until 14. And then now at 14, what do I do? To 15, you do tau 3. So this is 14 to 15. Now, at 15, here comes the interesting point between EDF and rate monotonic or deadline monotonic. At 15, I have how many tasks? I have this one and I have this one. This one has a deadline of 17. This one has a deadline of 16. So tau 3 wins in this case, right? So this is how I'm able really to meet the deadline of tau 3. You see the difference, right? In EDF, you favor tau 3 because it has a tighter deadline now, right? This allows you to meet the deadline of tau 3, which wasn't the case for deadline monotonic. Now at 16, what do? I have 2 jobs, in fact, this one and this one. Which one has a sooner deadline? The down arrow here is sooner, so I do tau 1. So I do tau 1 from 16 to 17. At 17 to 18, I do this one. And I'm done, right? So in this case, you are able to meet all the deadlines for EDF. Yeah, because if you think here at 16,
Yeah. 18 plus 1.
oh, let me think. What? There's something wrong here. So this one arrives at 16 and it has a deadline, so it should be 19, not 18. Because in fact, it has a relative deadline of 3. So you arrive at 16 plus 3, so it's 19. So you run from 17 to 19 and you should be fine. Questions? I'm hoping when you try this on your own, don't look into the solution, try to do it step by step. And then once you do it once, it's just done, right? Okay, great. So now we go to more interesting questions, the stuff that we discussed last lecture, which is multiprocessor scheduling, right? Now you have given so many tasks, which means no way you can really schedule all of these in a single processor. Then he said, assume that you have the following task set. All of these are periodic tasks. You want to schedule them on multiple processors using partitioned EDF. So in this question, I forced you to go to the partition class, right, of scheduling. And then the first point is you try to find a partition in which all the tasks are really schedulable and the number of used processors is minimized. So this is very key, right? Yeah, exactly. If I did not really give you this in the question,
Then it's very easy.
how many tasks do I have? 10. How many processors do I use? 10. And I'm done, right? It doesn't work that way. The real interesting part in multiprocessor scheduling is you don't want to use so many processors, right?
Yes.
So you want to minimize them. Now, how do you do this? Usually, one of the solutions, again, BFair was trying to balance things, but BFair is a little bit complex. So what I usually ask you to do here is to try to use a greedy algorithm. What we mean by a greedy algorithm is you try to make all the processors, in fact, busy all the time, right? So we'll see how do we do it. So in an exam, if you had the multiprocessor scheduling, just follow the same approach we do in this question, right? We'll see how we're going to do it. But first of all, if you think about it from a bin backing, last time we said this is a bin backing problem, right? Like this is again, you have limited number of bags and you want really to maximize what you put there, right? If you think about it intuitively, how you solve it, you want to start with the tasks of the biggest utilization, because these are the ones that really are going to determine. It's like saying, and you have a bag, you start with the heavy items, or like no, the ones with the largest volume, right? Because these are the ones that are going to determine what is left over. The ones with a small volume can fit in any of the leftovers, but the ones that are big simply are going to determine how many CPUs you need, right? So what we start in this problem is you order all your tasks based on their utilization. So first step again is to calculate utilization, right? So you start to calculating the utilization, and you basically, well, here I'm just calculating the utilization for you. Here. So you start by tau 1 again. You just do C over T, right? 3 over 10, 4 over 20, etc. So this is the utilization on the side. If you sum them up, and again, this is where the summation helps you, guiding you a little bit. We ended up with a total utilization of 3.7. Does it mean that no matter, this means that no matter what you do, what is the minimum number of CPUs you need?
You need 3.7 CPUs.
Yeah, but there is no, yeah,
0.7.
which means you need 4 at least, right? If you were ideal, you would use 4. So that means there is no point of trying and get 3. Because you might think of maybe I start with 1 CPU. If it doesn't work, I start with 2, 3. Well, there is no point because the physical utilization is 3.7, right? So this is at least we need 4 CPUs. So you start with 4. If it doesn't work, you try to go for 5, right? Then you start ordering tasks in ascending order according to the utilization for the rationale that I just gave you for the bin pack. Which one has the highest utilization? It's 10, which is 0.78. And what does 0.78 means? It means you need a 0.78 of a CPU, right? So it's more than 3/4 of a CPU. And then 8 is 7. Ascending order, yeah. Oh, descending order, my apologies. Should be from the highest to lowest. Yeah, should be descending order. That's wrong. Yeah. So basically 10, 8, 7, 9, 1, 1, until you go to tau 4, which is basically just simple 0.1, right? Again, the rationale is if you schedule everything and you're left with 0.1, it's easier to put in a CPU than if you are left over with 0.78, right? And from there, you start really scheduling things on in your CPU. So you start by saying, I started one iteration with 4 CPUs. In the first iteration, I start with the ones, piggyback on the ones with the highest utilization. So you put tau 10 in one, 8 in another one, 7 in another one, and 9 in another one. The reason I did not put 8 and 10 in the same CPU is because, yeah, they don't fit. Every one of these, like alongside every other one, does not fit, except maybe you can try to put T9 with T7, right? But it's better because T9 is the remaining highest utilization, is to put it in the 4th, right? Great. So we start, this is your first iteration, and I'm done with the first 4 highest utilization tasks. Are we good so far? So what we have done is order them in utilization order. I know I need at least 4 CPUs. Take the most 4 high utilization tasks and put them in the 4 CPUs. And then start seeing what is left over. Now, in the second iteration for tau, for the processor one that has tau 10, how much utilization you have left? 0.22. Do I have any remaining? Well, again, I'm done up until tau 9. Tau 1, what is the utilization of tau 1? It's 0.3. Now we start seeing where tau 1 fits. Does it fit in processor 1? No. Does it fit in processor 2? No, it has a utilization of 0.3, and here you're only having 0.25 left, right? So it doesn't fit in processor 2. Does it fit in processor 3? Yes, so you put it in processor 3. Okay? This is basically called the greedy algorithm, right? Again, this is one of the solutions to solve the bin backing problem iteratively. Okay? There is math behind it, but again, we're not doing the math now, right? And then what do I do? In the other iteration, I start with the one afterwards, which is tau 5. Now for tau 5, what is its utilization? It's 0.26. Now, what I'm left over with, I still have here 0.22, 0.25. Now with 0.6 and 0.3, I'm left with only 0.1. And then basically I have 0.35. Now for tau 1, I'm having 0.3. It cannot fit here. No, I'm done already with that one. With the tau 5, 0.26. 0.26 cannot fit here. It cannot fit here. It cannot fit here. So you're only left with processor 4. So you put it here. And you recalculate the remaining utilization, right? So here you are summing up to 0.61, which means you are left with 0.39. Okay. Then you go for the one afterwards, which is tau 3. Tau 3 is 0.25. It doesn't fit here, but it fits ideally here. You just put it here, which means your processor 2 is out of the equation. So you reduce the problem. Good. So we're done with tau 3 in that case. So I go to tau 2. Tau 2 is 0.2, but it also fits very nicely here, right? So I can put it here. Okay. And now I'm only left with 0.02, which will not fit any task. Then for tau 6, it is 0.13. It doesn't fit here. Here I'm done. Doesn't fit here, so I'm only left with this one. So you put it basically here, which is tau 6. And then for tau 4, also you only left places processor 4. So doing this, you manage to schedule all your tasks in 4 processors using the greedy bin packing algorithm. Yeah. Tau 4 can fit in B3. Tau 4 has a utilization of point. That's also correct. It can also fit here. That's correct. But if you, that's an excellent point. So now why don't we put it here and we put it here for balancing parts, right? So now if you put it here, you force this CPU to be utilization of fully 1, right? Which means when you try to schedule them using EDF later on, you barely make it, right? But here, this utilization is still further below 1, which means it's easier to schedule. So you try to push in more stuff there, okay? Yeah.
So ideally, you want to make it as low as possible each.
For number of processors, and you want to balance as much as you can. So these are the 2 key concepts: minimize your number of CPUs and balance the tasks among the CPUs as much as you can. Why we want to balance? Because the more the utilization, the harder to apply any scheduling algorithm, right? You mean here, right? You can also try. By the way, that's not the only one correct solution. This is also another thing, is that most of the time for multiprocessor scheduling, in fact, there are multiple correct solutions, right? Because your point is maybe instead of putting in processor 2, I put it in processor 4.
Yeah, processor 3.
This one, you mean?
Yes, this 0.
Like, which is that one, right?
Yeah.
Yeah, but then basically this one will fill in up faster, and then you have to push in more stuff to B3 later on.
Yeah.
So it's a balance, right? Yeah. So it's either way. And in fact, this is called the branch and bound problem. How a software will solve this? It's an iterative solution, right? You basically try to balance as much as you can in your next iteration. It's a graph-based algorithm, right? So in my next level, I try to balance, but the balancing is a heuristic. It's not really proven to be that's the best solution over that one. And if at any point I discover that I'm not able to, I go back and retake the other branch. That's on you. Okay. Cool. So now we go to maybe the harder part. After I do this step, yeah, scheduling. But the nice thing here is once you are done with this slide, you reduced your problem into a simple uniprocessor EDF, right? For every processor, the problem is as easy as for processor 1, I want to schedule 2 tasks, tau 10 and tau 2. For processor 2, I want to schedule 2. For processor 3, I want to schedule 2. For processor 4, I want to schedule 1, 2, 3, 4, right? So you take it basic, it's like solving a 4 uniprocessor scheduling algorithms, right? Okay, so now for processor 1, you have 2 tasks, tau 10 and tau 2, and simply which one is highest priority according to EDF. Again, it will change really from a job to another job. Tau 10, you have a deadline of 100 and period of 100, and tau 2, you have a deadline of 20 and period of 20, which means in reality, tau 2, well, first of all, you have 20 and 100. So what is your hyper period? My hyper period is always the least common divisor of the 2, right? I have a period of 20 and a period of 100, so it's definitely 100, not 5. Like basically the hyper period is where your full schedule repeats.
VLC, least common multiple.
Least common multiple. Oh, do I say it like the least common divisor? I confuse you, right? So it's basically, okay. So it's least common multiple, right? So it's basically take the one that you can divide both periods on. So you have, my apologies. I keep saying least common divisor. It's not correct, right? It's the least common multiple, right? Which is simply the hyper period is where your schedule repeats. So you take all the periods and you see how can they fully repeat. Now, if I have a period of 20 and a period of 100, I can repeat my full schedule every 100, right? Because this is how they align fully, right? It's no, not necessarily, because again, in the past we had 4 and 5. So in this case, you need to do 20, right? Because this is where you repeat, right? It's the least common multiple, right? This is what, yeah, least common multiple. Great. So now, which means my hyper period for processor 1 is 100, and which means also this is very easy to schedule, because always I will find which one is the highest priority between tau 10 and tau 2. Tau 2 always, right? Because tau 2 will always have, it has a deadline of 20 and period of 20, right? So it will always have a deadline smaller than tau 1. This is why you find we start by scheduling tau 2 at 0, at 20, at 40, at 60, and at 80. Once I'm done with that, I basically take the rest, right? And I find that I'm always busy and I meet my deadline, right? Good. Now for the second CPU, I have two tasks, 8 and 3. For 8, I have a deadline of 400. For 3, I have a deadline of 100. Yeah, tau 3, and my hyper period is 400. In that case, I have 100 and 400, so it's 400, right? So you start again at 0, 100, tau 3, 200, 300, 400, and then you take tau 8 in the remaining ones, right? So you observe that when I give you a multiprocessor scheduling question in an exam, I try to make the uniprocessor scheduling quite fairly easy. You don't do a lot of switching, right? Because simply you have already spent some time with the question, right? Okay. And the most interesting one will be the last one, because this is the one that has like a large number of tasks. Then for B3, I have 1 and 7. For 1, I have a deadline of 10, period of 10. And for 7, I have what? 200 and 200, which means my hyper period is 200, right? And then which one is the highest priority always? 1, right? Tau 1, because it has 10. So it's like at 0, I schedule tau 1, at 10, at 20, at 30, etc., 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 right? And then you schedule tau 7 in the leftover. Yeah. Yeah, for this one, okay, do you do it for 400? It's too much, right? But the point is, this is EDF. So you know for sure you have a schedule because your utilization is equal or less than to 1. So I'm not worried, we are not worried about missing a deadline, right? So if you tell me that this is basically how things repeat, and then I put tau 7 in the leftover, this is how you continue up until 400. But if you want an exact value of where you should really stop, it should be 400, right? But in an exam, that's too much. So if you tell me, okay, this is just repeats, I know you understand what you're doing, and that's it. Okay. For the last one, I think, for the last one is the most interesting one. Let's again see if we have time. Yeah, so we can do the last one together. So for last one, I have 9 and 5 and 6 and 4, right? So for 9 and okay, maybe in fact we can even put this as if it's an independent problem. So I have tau 4, tau 5, tau 6, and tau 9. And then I have C, D, and T. For tau 4, I have 3, 30, 30. For tau 5, I have 13, 50, and 50. For tau 6, I have 13, 100, and 100. For tau 9, I have 7, 20, 20. First question is, what is my hyper period? Without tau 4, it would have been very easy, right? But with tau 4, because it's 30, this is quite tough, right? But you have 30 and 100, so that's easy to decide as well. It must be 300, cannot be less, right? So 300. So you have a hyper period of 300, basically, right? Now, let's see if we try to put in like a 300 and see if that works. Now, which one has the smallest periods? It's your tau 9, right? Which is 20 and 20. So now you have here 20, 40, 60, 80, then at least 100. This is for tau. This is for tau 9, right? So tau 9, tau 9, tau 9, tau 9, tau 9. Okay, so then what is the one after? Is tau 4 is at 30, right? Why I'm having 27 here? What's like 27 really mean? Maybe I should we should do it using 4. So let's just give me a second. Okay, that's not good. Okay. Okay, so let's try to do it. You guys are backing up very early, so we still have 7 minutes.
Most of the Sunday.
So you want to back up early for the rest of the week because of Sunday? Okay, so we have tau 4, tau 5, tau 6, tau 9. Now for tau 9, I have again 20. I try to back it up 40, 60, 80, 100. Let's see if we can stop at 100. And then for tau 5, for tau 4, I have 30. Should be 30, then 60, and then 90, and then 120. So maybe I just put this one also as 120. And then for tau 5, I have 50. So it's here. And then I have 100, which is here. And then I have 150 somewhere here. For tau 6, it is the one with the 100, right? So I just put it here. And then I have a 200 later on. So let's start scheduling things one at a time. So here I have one nice thing about this is that I have the red lines equal to the periods, right? So it's easier to decide. At time 0, which one should go? I mean, with putting this drawing, it's very easy to decide, right? It's tau 9, right? Quite easy. Because that's the one that comes first. For how much I should execute is for 7, right? So execute from 0 to 7. Now, and I'm basically done, right? So I switch to the second one, which is tau 4. Tau 4 should execute for 3 time units from 7 to 10. Then I go to tau 5 because it's at 50, and I execute for 13. So it's from 10 to 23. Good. Now I'm done with tau 5 at 23. I should go to tau 6, which is the last one. It executes for 13. So from 23 to 36. Should be. Oh, I'm not very aligning, right? But excuse me for this. So it's simply here up until we said what?
36.
36. Okay. Oh, no. Sorry. Give me a second. I think we skipped many decision points, right?
Yes, there was one at
Doesn't help me erase. Okay, so maybe I'll just use a different color then. So in reality, at 20, we should read. Come on. Yeah, let's see if the decision will change. At 20, here I have this one. This one should go, right? Yeah, but I'm not really able to draw. And if I exit the full screen,
if you exit the full screen and save the.
no, I have to really. This projector is very odd, so I have to duplicate again. Okay, let's see. I raised this thing. I'm not even able to draw. Okay, so I will leave this for you. I will give you the solution. But the key idea is this one turns. So what we want to give you out of this multiprocessor thing is once you reduce it to a single processor, You should really be able to solve it using EDF or rate monotonic or deadline monotonic, right? So one example question in the exam is you start with multiprocessor, and then I ask you do it using DM or EDF. Now, one last thing is that we did not solve a problem using global scheduling yet, right? So global scheduling is harder to decide. So if we did not really have the time to go through one, I will try next one. Then you think that global scheduling is not really part of what you should be asked for, right? Because I think if you solve a global scheduling problem in an exam, it will take you a lot of time. So I'm still really weighing the odds. Should really I give it to you and exam you on, or should I give it to you and not exam you on, or not give it to you at all?
You can do it, and you can ask us only for a part of it.
Yeah, the problem with global scheduling is it's global. So I cannot really partition it like this one, right? But at least you see how to solve a partitioning problem, right? So yeah, you will take 3 minutes back and I will post the solution for you. Thank you.